of this video conference, I will take a few minutes to present you the Académie de Marine, the French Académie de Marine. French Académie de Marine was created in 1752, suspended in 1793, and reborn in 1921. It is a public organization linked to the Ministry of Armed Forces. Its mission is to promote high studies contributing to the development of maritime sciences and activities. That's somewhat administrative language, but well, involved in everything concerning the sea and the ocean. It comprises 78 French elected members, 20 elected foreign members, among whom there is an eminent Swedish member, Lars Vedin, who our friend, our Swedish colleague surely know, and what we call about 200 permanent guests, who of course will work with us on most activities. And we cover all maritime domains. We are under the supervision of the Ministry of Armed Forces, but we deal with all maritime domains, not including, of course, the military. Our actions and products, well, we organize short conferences, about 12 per year, studies and reports, a lot of them, for instance, well, I don't make that, but in very numerous subjects. And the reports can be found on the internet site. There are long conferences, like the one I talked about, about the automation of ships and aircraft. We award prizes, quite a lot of them. You can read some detail on the slide. We organize study travels in France and abroad. Normally 2 per year, but not, of course, last year and this year, while it's also compromised. We publish a monthly internal bulletin, a bi-monthly newsletter, a trimestrial communication, well, in French, communication et mémoire, I think you can understand it. And we, of course, we have an internet site. And, well, you've seen that we were reborn, as I wrote, in 1921. So this year that will be 100 years ago, and the centenary is a good opportunity to think about the maritime challenges of the next century. So, and we hope that other European academies can participate in our thinking. Before giving the floor to Jean-Marc Garot, I give you a few words about Alain Bovis, who will present the Académie de Marine part of the report. He is a vice president of the Académie de Marine, and that means that he is the future president, beginning in the autumn 22. He is an authority in naval sciences and engineering. He graduated from École Polytechnique. He has a PhD in hydrodynamics. In the Ministry of Defense, he did studies about the attacks of the future, but now they exist, but attack submarines. And he held several high-level positions, reaching the 3-star level. He joined Naval Group, there's another name, but now it's Naval Group in 1997, where he was the managing director of its propulsion systems branch. He was CEO of a joint venture with Thales, and from 2009 to his retirement in 2014, he was science and technology director of the group, and he's still teaching and consulting. So now, I will give the floor to Jean-Marc Garot, but a few words about him. He was very instrumental in all the work we did on this subject. And in particular, he put together the Dossier 50. Well, that was really a tough job. And so Jean-Marc, well, congratulations and still many thanks. So now the floor is yours, Jean-Marc.
Thank you.
Okay.
You know?
Oh, okay. Thank you. Okay. Well, good evening to everybody. I'm Jean-Paul Troadec. I'm a member of the Academy of Airspace, and presently I am the chairman of the section 3 chaos with pilots and operational issues. So I will briefly present you the Académie de l'Air et de l'Espace. Of course, we are a very young academy compared to the Maritime and War Sciences Academy in Sweden and in France. We have been created in 1983 under the initiative of André Turca, which is a well-known first test pilot of Concorde. Our aim is to promote the development of high-quality scientific, technical, cultural, and human activities in the field of air and space, either civil or military. We organize visits for members in our aeronautical and airspace seats in France and Europe, conferences. We deliver prizes and publish the conclusion of our work in the shape of dossier and opinions, and we publish a bi-monthly newsletter. Our members have a wide variety of backgrounds coming from industry, operators, administration, university, and represent a wide variety of experience in the field of aviation of space. We are open to European members, which represent 1/3 of our members. 4 of them are Swedish, and we are happy to have to this conference the presence of our Wergermark, who was at the initiative of this conference. Next slide, please. As regards the aircraft automation, and to underline the type of dossier we are publishing, you have the list of all the dossiers which have been published in the last years in the field of aircraft automation. You see that it's nearly 1 per year, and we can access to this dossier freely on the AA website. We have the address of the website on this slide. This year, the focus were, of course, more on the climate challenge, and also you can access to this conference on the AA website. Next slide, please. On Dossier 50, we are speaking this night, has been published very recently or on the AA website, and of course you can access freely to this dossier. Next slide, please. On the aviation, I will discuss the aviation aspect of this dossier. For clarity, we have chosen today to present separately the aviation and the maritime aspects. Also, they are presented jointly in the dossier to underline the similarities and differences between maritime and aviation activities. As regards specifically to aviation, it is focused on commercial aircraft and develops the following aspects regarding automation and autonomy. The objective of automation, the technical aspects, economy and acceptability, cyberspace, artificial intelligence and certification, legal issues, and as regard air transport safety, the human contribution will be presented by my colleague Bertrand de Courville after my presentation. Next slide, please. The objective of automation, they are the same since the beginning of aviation. The first one is to assist crew to manage systems increasingly complex and to improve access to flight information. This has allowed a progressive reduction of the crew from 4 to 5 at the beginning of commercial aviation to 3, and then today to 2 crew. The last operation being this of the flight engineer, thanks to the automation of mechanical systems. Autopilot is of course an essential device amongst automated systems. Its function are being progressively sophisticated from simply keeping course and altitude to possibly managing the interflights. Automatism have also been developed function devoted to safety, such as flight envelope protection, traffic avoidance, runway excursion prevention, as Bertrand will develop later on. Next slide, please. Here you have a slide, a picture of the cockpit of the A350, which shows the graphic interface developed for this new version of the Airbus. And you can see the pilot dialoguing with the computer. Next slide, please. What is the situation of autonomous civil aircraft today? As regards autonomy, the only so-called autonomous civil aircraft flying today are limited to light aircraft. I say so-called autonomous because, in fact, they are flown by a ground pilot. These aircraft are subject to strict limitation as regards their size, the airspace they can fly, with specific training requirements for the pilot, depending on their use. Many larger drones carrying freight or even passengers are under consideration, but none is presently in operation. Most of them are electrically driven, devoted to urban mobility, and EASA is developing certification rules for this type of aircraft. On the picture, you have a picture of such an helicopter. Next slide, please. As regards the military aircraft, on the contrary, armies still operate a large drone for military and observation purposes. Some of them have the size of commercial aircraft. These aircraft fly in a specific framework compared to civil aircraft. They are subject to different certification rules, and they use specific airspace, and of course, they carry no passengers. Nevertheless, we can think that their experience will be useful for developing large commercial drones in the future. Next slide, please. Today, all large civil aircraft are operated by a two-pilot crew. Is it possible to reduce the number of crew to 1 or even 0 without decreasing the safety level? Two ways are under consideration by the manufacturers. For long-haul flights, when a crew complement is needed above 2, the perspective could be to suppress the third man. This meaning that during some cruise phases, the aircraft can be operated by a single pilot for limited time, of course. For short-haul flight, the suppression of the second pilot should require a new type of assistance under normal operation from ground or board, and a recovery system in case of pilot incapacitation, such as developed by Garmin for business aircraft. Here you have a view of what could be a single pilot cockpit. Next slide, please. Single pilot operation does not seem to be a priority for most operators, in particular because the economic benefits are not demonstrated and the public acceptability questionable. On the contrary, some support the crew complement suppression as long as the safety is maintained, in which they see an economic benefit and a simplification of crew planning. Next slide, please. It's clear that the threat, the cyber threat, increases with the development of communication and electronic devices, as discussed in our dossier 45. The following graph picture the connection inside the aviation system between aircraft, satellites, ground station, air traffic control, and so on, which means that all actors must develop an action plan coordinated under the auspices of ICAO. Next, please. This is a graph of the different interaction between the aircraft, air ground, ground station, satellites, and it gives an idea of the level of threat, because there is a threat, of course, at each connection between the ground and the aircraft and the satellites. Certification. The certification of artificial intelligence is a new problem for the aviation, because the introduction of some level of learning-based intelligence, as opposed to the traditional deterministic algorithm approach, requires a complementary certification model. The normative framework based on compliance with rules designed to ensure the required level of safety must be complemented by an approach based on risk analysis more suited to innovation and consideration of probabilistic factors. Next, please. My last slide refers to legal issues which have been discussed during the conference. The question is the determination of responsibilities in case of accident, facing the increased complexity of interaction between the different systems and actors. The responsibilities will necessarily fall under the same actors as today: manufacturers, operators, safety authorities, but will probably be more difficult to determine. This could be a problem in case of criminal investigation, the question being the same for the determination of causes by the safety investigators. Nevertheless, insurance mechanisms make that victims can be compensated even in the absence, and certainly. And now I give the floor to my colleague Bertrand.
Thank you, Jean-Paul. Are you hear me, Jean-Marc, Jean-Paul?
Yes, perfect.
Okay, good. Thanks. My name is Bertrand de Courville, and I'm a retired captain from Air France. I've been flying for 30 years, and I was involved for about 20 years with safety issues at the Air France level and also international level. And I made this presentation at the conference organized with Jean-Paul. So when it comes to working on air transport without pilot, it's good to look at what pilots do, and more particularly, what is really the pilot contribution to safety. Next. So what we see for about nearly three decades, so more than 25 years, is that a very significant improvement of safety. Now, depending on what we look at, what kind of statistic we looked at, airlines are now 4 to 5 times or even more safer than they were 25 years ago. The question is, how do we explain this? Next. And one way to answer is to look at what changed in 25 years and what remained unchanged. So about what remains unchanged, airplane reliability, no change. The planes are today as reliable as they were, nearly the same, no change. Failure, anomalies, poor weather, still part of daily operation that it was 25 years ago. Human errors, the same. There are pilots, air traffic controllers, maintenance, and many other actors are making errors. Something interesting to say also is that as it was 25 years ago, the critical safety decisions made in real time, short-term decisions are made by pilots in flight. It's still the case today. Today, as it was 25 years ago, it's two-pilot crew, as Jean-Paul mentioned just before. And something that few people really knows is that 99% of the landing are performed manually. Approach may be flown without autopilot, but in 99% of the case, the landing is performed manually. So every flight is a source and opportunity of training to fly and land manually with any kind of weather, with the exception of fog, of course, where we require auto land capacity. Next. So now, what really changed and what could be the source of this very significant improvement of safety? We have, for these 25 years, improved really significantly the design of decision aid, and mostly those related to specific risks, those who were the major contribution of accidents. I'll say a few words more about that. We have a very more efficient teamwork today. Teamwork in the cockpit is on a fail-safe mode, which is part of the concept of every aircraft component, but it applies also to the crew. If one component failed, the other one is there as a backup, and it's the same for the crew. We have many sources of training that are more and more sophisticated. Initially, we had a crew resource management training, as it was the case in the ship industry. I think bridge resource management is all there. And more recently, we have a threat and error management, which is a very efficient way of addressing risk at a short-term level in the cockpit. We have a Troadec, which is an acronym about how to make decisions in a critical situation, and we train the crew to work together with that, and also to get information beyond the cockpit when needed. We have a more efficient feedback process, pilot reporting, flight data monitoring, recorded flight data monitoring, which is systematically analyzed and collected at the airline level. And we have incident analysis and many more sources of feedback. And all this give a better dissemination of operational lessons through the industry. And maybe I would say one of the most important evolution is what we call the safety management system, which brought a very formal, explicit way of addressing risks. And it is a model, a way of addressing risks that is shared and regulatory required for airlines, flight operation, training, maintenance, but also about airport operation, air traffic control, and the same model is used at the authority level. Civil Aviation Authority have now to address the risks the same way, and it brings a common language, a common processes, and the different actors which were used to work separately on risks now work with the same kind of model and language, which is quite efficient, I believe. Next. So a few examples of decision aid and automation regarding a specific risk. Next. We have here the ground proximity warning system, which is an old system designed to avoid a collision with the ground. And about nearly 20 years or 15 years ago, it has been improved in what we call enhanced ground proximity warning system, which informed the crew about now more in advance about the possibility of a collision with the ground. And now the control flight into terrain, as we call this kind of accident, is nearly eradicated. Next, we have an important aid about decision is the detection and the way to avoid wind shear, which is a quite important risk source of accident, loss of control related accident. Wind shear warning system now is equipping all aircraft. It's required per regulation. Next. Also, we have now, because of those type of accidents are now really reduced, we have to look carefully about runway overrun and what we call runway excursion. And there are different equipment that are now on board to inform the crew when there is a real problem of energy, just as the touchdown or in advance, when really the energy of the aircraft will be too high compared with the available distance or braking capacity of the aircraft. So it's all, again, a decision aid to go around and to try another landing. Next one. And of course, traffic collision avoidance system, and which is in place since about 20 years. And now it's connected with the air traffic control system, and the air traffic controller and the crew are trained on a regular basis to bring the correct response to a traffic collision avoidance alert. Next. So the main contribution to air transport safety were used to think about and look at this model, which show how today we understand accident. It's not a single cause, it's a multi causes model, where at the front line, there are, of course, pilots and other frontline actors, but here we are talking about pilots. And one aspect I presented here is that two pilots is a fail-safe concept. And if one fail, if one make an error, and if the crew is well trained, really much mature about that, the error will be corrected. But also we have this feedback process, which is well in place, that is improving today, and that feed all the level of the air transport system. Next. Oh. So what the pilot are doing? Just back. Could you go back? Back. No. Could you return on the? Ouais. Again. Okay. Well, so pilots are actors and witnesses, and a few words about what they are doing really in the cockpit. They are trained to manage any type of incident in flight and land the plane and with its occupants, of course, on a secure place. They are empowered in case of unsafe situation to abort, to take off or landing, or to divert or to evacuate. I said before, they are there and they are making the decision to do that, and they're trained for that. They are empowered to do that. Interesting to say also that they are independent enough to reduce the risk of biased decision when it comes to cost or things like that. Biased decision exists there still, of course, but they are quite independent. They are trained to be independent from those cost constraints and to make the decision really based on safety. They also are trained as a team to detect and correct any time of error, their own error. They learn, a young co-pilot learn to speak up when a captain is doing something wrong. And if they don't do that during a simulator session or during a check ride, they will have bad marks. So they will be judged for that. Also, something very human we have to take into account when we look at unmanned aircraft. It's that the men in the cockpit are able to maintain a reasonable level of paranoia, which is a way to say that they are the risk in mind. And because they are human, they think differently than a machine. And of course, as I said before, human are a unique source of feedback about every aspect of their flight because they are on board. Next. So an example of a sample of events, there are two slides about that. Next. This is a single month in November 2019 for the conference where I spoke. I looked at the event we had during a single month in 2019, and this is an example of what happened in flight in different countries around and airlines around the world. It goes from maybe engine failure, a lightning strike, fume in the cockpit, or heart attack in the cockpit. All this done in flight. Next. And this will have to be done and to be managed by the crew sometime on a very short notice, and they have to do things in they don't have much time to make a decision. So this is one of the main difference between the air transport and other surface type of transport. When you are in flight, we have a limited time to go down and to land the aircraft. We cannot wait for any kind of support, of help, and so on. And that's really the main difference of what we are doing in flight operation. Next one. So this brought some studies, and one interesting is done right now. the team is publishing articles and studies about the real contribution of the crews to safety, why we don't have some much less accident today, and not only why we have accident. When you look at this circle on the left side, there are it's clear that we have very, very few fatal accidents. So what about all those flights without accident? In fact, there is a lot of things to learn about that if we want to think about automation. Next one. Well, as a conclusion, we could say that by concentrating on what people do wrong, it was the case and it's still the case, it's understandable. What people do wrong to explain accident, but they are very rare. We have been missing opportunities to learn about what they do to have safe flight, what they do right. And the work dedicated to future single pilot version and fully autonomous commercial flights has uncovered unknown aspects of air transport safety. The human contribution to unsafe situational recoveries have been underestimated and need to be better understood. I would like to call Claude Delay, who was an engineer and test pilot at Airbus. He was the Airbus Director of Flight Test Program, and he was in charge of the Airbus 380 program. He said that the idea that because pilot error is the main cause of accident, replacing pilot by computers will improve safety is an absurd reasoning. It's quite obvious. Nobody knows, in addition, he said that nobody knows how many accidents would be caused by computers due to human, again, errors in software programming, for example. Thank you.
While...
Ah oui.
C'est bon? It's okay. Alain?
Okay, good evening, everybody. It's my privilege tonight to speak to our colleagues from Sweden on the maritime aspects of autonomy and automation. Well, in the maritime domain, the perspective of seeing autonomous unmanned ships sailing for commercial or military purpose has been contemplated for several years now. And the International Maritime Organization, the IMO, has proposed a name for these vessels, which is Maritime Autonomous Surface Ships, or MASS. Next, please. Well, unmanned vehicles are already a reality in navies. Several unmanned boats are being used for surveillance or intelligence gathering. They are remotely controlled from the shore or from a naval ship. And mine warfare is one of the most developed warfare domains for unmanned vehicles. And for example, within the bilateral UK-France program of mine countermeasure, the program called MMCM, it is anticipated to have a system combining an unmanned surface vehicle carrying an underwater unmanned vehicle far into the mined zone with the purpose to localize and destroy the mines, keeping the operators and the controlling ship far away from the risky area. The US Navy, for example, plans to design and field a range of unmanned ships, large and medium size, capable of deploying deep into contested waters for far in front of crewed ships to hunt mines or to monitor China's ships and submarines and launch ship-killing missiles. This US Navy is quite right now this month running a major operational exercise that will see medium unmanned surface vessels, medium size, like the Sea Hunter on the picture on the slide, to run through drills controlled by the cruiser USS Zumwalt. Next, please. Considering the civil sector, which is of matter of interest for the industrial community and regulatory bodies, automation and autonomy need to be precisely defined. Different levels are defined according to the navigation area considered, for example, short sea shipping or long-range journeys. To the degree of automation, i.e. the decision-making share between embedded software and human operators. And finally, when the ship is remotely controlled, the degree of control from remote manual operators from remote manual control up to mere soft supervision. The feasibility of remote steering from 1,000 miles distant virtual bridge has been demonstrated last time in September 2020, when a French Navy oceanic tug has been operated from a control room, virtual control room located in near Paris, 1,000 miles away. And another example is the Norwegian company Kongsberg has recently designed and built an autonomous container ship for a shipping company named Birkeland, and the ship is the Yar Birkeland, the picture on the slide. This ship is actually tested at sea and is supposed to enter in service later this year on a local line in Norway on a pure autonomous mode. Next. Predictive big data analytics, Internet of Things, Internet of Services are new means to anticipate markets, to treat orders, traffic, sea state, and to optimize fleets, cargoes, routes, loading, and discharging operation of the ships. The shipping company doesn't envision today, like the aircraft company, the air transport company, to eliminate completely crews, embarked crews at a large scale and for long journeys. Instead, the maritime transport community is expecting significant benefits from an increasing automation of ships and of their operations. On the safety side, potential reduction of human errors, taking into account that digitalization can raise new risks in this operation. For the protection of environment, by optimizing the performance and the powering needs of the ship travel and operation, navigation and operation, and given a competitivity advantage to the companies who will go towards this automation and autonomous shipping. Next, please. More precisely, the economic objective of shipping companies is to achieve a seamless multi-modal transportation door-to-door, including, of course, the seagoing segment, but also the other forms of land transportation, and reducing unuseful waiting time, improving productivity of loading and discharging operations, optimizing routes according to real-time weather information, etc., etc. Next. Thus, automation and furthermore autonomy have to be approached in a holistic global way, from planning of missions to actual operation of systems and ship steering. So the whole chain of the concept of the system has to be taken into account at the same time. Any automated function must use data provided from other systems, automated or not, and has itself an impact on decision making in other domains. Thus, interoperability and interconnection of different functional systems have to be carefully taken into account. Next. Several hard points are still ahead of state-of-art technology. The maritime domain has not as much as aeronautics the culture of quality development of software, especially those related to ship safety as navigation or stability. Existing software are often poorly documented and the operators not sufficiently trained to overcome software limits or deficiencies. The performance and integrity of communication and data communication systems and data links between the ship and the shore are crucial. Artificial intelligence is often considered as providing solutions to any future problems. If big data analytics is already integrated into many automated systems, machine and deep learning may lead to situations where no human operator will be able to understand the machine decision-making process, which might be quite a problem in emergency situations. Next. In an highly automated ship, even more an autonomous ship, the number of software impacting the safety of the ship and of other vessels and environment is increasing. The validation and certification of these pieces of software would require statistics collected on years or decades of experience, which is not realistic. Instead, we must rely on detailed and internationally acknowledged standards that have still to be promulgated. The regulatory bodies and certification companies must then work to strengthen and enforce the new standards. The ship is a node that interacts with many other actors, private or public authorities. The interoperability of the various systems related to these different actors through standardized interfaces remain also largely to be acted. Next, please. If we talk about safety, the numbers of shipping accidents and ship losses are decreasing over years, but this number still remains to be further reduced. It is said that most of the accidents are related to human errors. It can be navigation errors, poor maintenance, inappropriate handling of cargoes, or others. Of course, these accidents could be avoided with automated systems. But as was said previously, digital technology may also introduce new risks, and especially when human operators interact with automated systems and they don't understand each other. Next, please. One of the major new risks brought with automation are cyber risks. We all have heard about recent spectacular and costly cyber attacks on shipping companies or port terminals. Recommendations and regulations are being developed by IMO, ISPS, International Ship and Port Security, and by European Union or by classification societies. This new regulation and new practice are to be applied by all the actors, the operators, but also by the software developers. And a long way is still to be done. Fleet and port operation centers already in each shipping company are planning and monitoring operations of the fleets. With the proliferation of onboard sensors, satellite observations, and data links, onshore control centers receive infinitely more data than the ship and its crew can process in real time. With automation and reduction of embarked crews, these centers will take an even more important role in ship navigation, propulsion regime control, loading, offloading, maintenance, etc. Thanks to the digital twin, the shore-based centers will be able to simulate and optimize any intervention at sea by the crew or plan maintenance work at port. Thus, the overlap of responsibilities between the ship and its crew and shore operation centers has to be clearly defined to avoid bad interaction between them. Let us talk about ports. The ports are logistical hubs in the transport chain. Nearly 50,000 ships transport over 11 billion tons of goods each year through the ports. A port is a complex area involving many players, and the development of digital technologies is profoundly changing the relationships and the respective responsibilities between these different actors. The question is, each actor is developing its own digital systems, but these systems, will they be able to talk together with standardized interfaces? This is the question. We can also see that drones are one of the components of the digital transformation, and the picture on the slide shows a prototype of a shore-to-ship drone designed to deliver some cargo from ships to the shore by air. This is an Airbus project for the port of Singapore. From the social point of view, a recent study from the World Maritime University in Malmö, Sweden, shows that automation will not reduce the global demand of personnel in the maritime activities and industry, but the nature of many jobs will shift from embarked physical work to ashore office work. Such new jobs may be more attractive for young or female students, but the challenge will be how to transmit to this new personnel the seafarers' experience when they will have less opportunities to sail. According to a recent survey, the digitization of the maritime transport raised a strong social reluctance. According to a recent survey done in France, 84% of seafarers that were questioned through the survey believe that automation is a threat to their jobs. And 66% of them think that the introduction of new technologies holds no benefit for maritime transport, which shows that there is a long way to go to convince all the actors and trade unions of this evolution. Next, please. And finally, we will have a look to the legal framework that has to adapt to technological developments. This is something very comparable to what was said for the air transport. From the authorities, the regulatory framework has already begun to be adapted to the new situation where experiments at sea of unmanned ships are now multiplying. IMO and the European Union have issued guidelines for this kind of trials. IMO has also engaged into a scoping exercise aimed to identify regulations that will have to be amended to take into account unmanned ships. From the legal point of view, in case of accidents, the liability will evolve as a broader range of players will be involved, as for example, the system manufacturers and the software developers. The search for responsibility is then going to be more complex, and the cost of insurance will probably increase. But the law will adapt and will not be an obstacle to autonomy the time coming. Last slide, please. Okay, this was my last slide. So we are open to questions if you have some, and we will be pleased to try to answer.
So the floor is open. Who is bold enough to ask the first question?
Not a question from Sweden, Anders Grenstad here, but thank you very much for very interesting briefings. I learned a lot in just listening to you and seeing all these slides. But as a question, how long time